this day and Monday to talk about our next section, 5.1. What we've been doing in the first half of the course is learning the mechanics of how to find a derivative. And now we come to the second half of the course in what's this stuff good for? So the first application that we're going to be looking at is graphing. The behavior of the derivative tells us something about the shape of the graph. Why do we care? Well, maximum revenue is where you have, we called it a critical point, where the first derivative is 0. Where would marginal revenue be decreasing? Where f prime is negative. So the idea about knowing the graph of a function has many practical ramifications. And so now what we're doing is basically terminology. What we want to do is start with a function and then come up with its graph. But for now, I'm going to do the other way around. I'm going to tell you what the graph of the function looks like, and then why it's important. How does it relate to the function? So indeed, I'm just taking, they call it example 3. This is just example 3 on page 298. We are going to see that if you've got a cubic function like this, it looks like the following. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. I'm just measuring my axes, and so 1, 0. And 2, negative 3. And so for this example, to get us into it, they've drawn the following for us. Okay. And we're going to see that in general, a cubic curve has that kind of sideways S. You see why I call it a sideways S? It's got that sideways S curve, that shape. And so what I want to do now is give you terminology. How do you describe this graph? Well, here I have what's called a local maximum. And we've talked about a critical point already. We've already seen that if you take the derivative, in this case it's 3x squared minus 6x. If you take the first derivative, and if you ask yourself what values of x will make the first derivative 0, if you set the first derivative equal to 0, you come up with these critical points. So can I factor a 3x out, leaving me an x minus 2? And remember, we talked about this the other day. The only way a product is 0 is if one or both of the factors is 0. So if you've got a 3x times x minus 2, there are 2 values of x that'll make this 0. X could be 0, or x could be 2. So we would say that there are 2 critical points at, well, x equals 0. When x is 0, 3x is 0, makes the product 0. Or x could equal 2. 2 minus 2 equals 0. And In order to get the y coordinates of these points, what do? You take the x coordinate and you put it back into f. F of 0. So if you put 0 back into f, you get 1. And here, how do you get the y coordinate? You take 2 and put it back into f. Isn't that 8 minus 12 plus 1? Isn't that 8 minus 12 plus 1? Isn't that your negative 3? Okay. So we found these two critical points. Notice that this one here is given a special name. Really, what I'm doing now, it's more vocabulary. You're coming up with a vocabulary in order to describe this graph. Because where we're going, we want to start with just, where we're going with this, is that we want to start with just the function itself, and then come up with a picture. So for right now, I'm sort of giving you the picture in order to talk about the vocabulary. We call this a relative maximum. We say that there is a relative max at x equals 1. You see why it's a maximum? Because it's larger than all of its neighbors. It's at the top of the hill. That's why it's a maximum. The word relative means If you go way over here on the right, there are y coordinates which are bigger. So this graph, as it stands, this has no absolute maximum, because this arrow just keeps on going larger, larger, larger. So this thing has no absolute max. Absolute means that its y coordinate is larger than all y coordinates on the graph. And as you can expect, this point here is called a relative minimum. Why? Because it's the bottom of the valley. Its y coordinate is less than the y coordinate of its neighbors. But again, it is not absolute, because way over here on the left-hand side, that's getting smaller and smaller and smaller. So we say that there is no absolute minimum. Okay, now, more vocabulary. Let me take some colors here. Yeah, let me first use light colors, so pink. This is a pink highlighter, and I'm highlighting this portion of the graph and this portion of the graph. Those two pink pieces are important. Why? Because the marginal revenue is increasing on these pink pieces. So, as the x coordinate increases, the y coordinate increases. These two pink pieces, they are called increasing. This shape is called increasing. And so where have I highlighted this in pink? It's increasing for x is less than 0. So for all of these x's over here on the left-hand side, that shape of the graph is increasing. Also, over here on the right, for all x is bigger than 2, it's increasing. Now, let me take some orange. And so I'm using an orange highlighter here. stare at the orange part of the graph. Do you see, those are interesting because there, for all of those x's, your marginal revenue is decreasing, right? As x increases, these orange y coordinates are decreasing. So we call that shape decreasing. So this is decreasing for x's between 0 and 2. There's more coming. There's more coming. But for right now, I want to show you how to set out this information in a table. How to set out this information in a table. So we're talking about shape. Increasing, decreasing, that's what we mean by shape. So you call this a shape table. And the shape table, it has intervals. And it has shape. And I need to tell you how to test. How do you test for shape? So, do you agree with me that I've got an interval x less than 0? And I've got an interval between 0 and 2. And I've got an interval to the right of 2. These are the three intervals that I have located on my graph. And judging from the picture, you agree with me that here in this pink interval, the shape is increasing, which we just abbreviate INC. And here in the orange, you agree with me that that shape is decreasing, that we abbreviate DEC. And here on the rightmost pink, that is increasing again. So I could have written these words here in pink, in pink, in orange. Okay. So, well and good. I have so far gone from my picture to my intervals. Fine. But our goal is the other way around. You want to be able to get these intervals in order to draw your picture. So I need to give you a test. How do you test these intervals to tell what their shape is? And I want to convince you that you test the first derivative. And let's look at the picture and see if I can convince you. Look at any pink point there on the left. Remember that the derivative is the slope of the tangent. So the marginal revenue, it's the slope of the tangent. And you agree, positive slope goes from the lower left to the upper right. So here, if my ruler is expressing the tangent lines, do you see that the first derivative is positive? That is the test whereby you know the shape is going to be increasing. If the first derivative in that interval is positive, you got an increase in shape. And can I convince you, you only need to test one point. You only need to test one point in the interval. Because if it changed. If you had an interval where the slope went from positive to negative, wouldn't you have to have another critical point in between? Remember we're talking about throwing the baseball up in the air? As long as the baseball has positive velocity, it's rising. When it has negative velocity, it's falling. Therefore, at the top, it's zero. So, if your first derivative goes from positive to negative, that's going to create a critical point, and there isn't another critical point in that interval. So, you only need to test 1 point per interval. Because otherwise, you'd create another critical point. And you know there are only 2. And likewise, for a pink point over here on the right, take any pink point. Do you agree? All of those pink slopes are positive. Lower left, upper right. And now how about the orange part? Take any orange point. Its tangent is slanting the other way, from the upper left to the lower right, meaning that its derivative is negative. So the pink derivatives are positive, and the orange are negative. And let me just take a look at something. Okay. 5.1 is dealing with just these critical points, increasing and decreasing intervals. I probably shouldn't even say this, but I will. 5.2 is going to get into another aspect of the graph. I probably shouldn't say this yet, but do you see this part of the graph from about here to the left? Isn't that bowing downwards? And from about here, isn't that bowing upwards? Or old books would say, you know, if this here were the cross-section of a bowl, the bowl would hold water. If this on the left were a cross-section of the bowl, it would spill water. So I shouldn't even be saying that at this point. 5.2, we're going to be doing the same kind of thinking, only in terms of the bowing, called concavity. But that's for like Wednesday. Okay, now, here's what I want to do. Yeah. So what I want to do is I want to, I started with the picture in order to give you the terminology. But that's not what we want to do. What we want to do is start with just the function. Take its derivative, get the critical points, and then get our shape intervals. That's what we want to do. So let me do a problem that way. So 5.1. Yeah, so you're assigned for homework problem 13. Let me do problem 14 as an illustration. So this is just problem 14 on page 308. And all they do is that they give you the function, f of x. In this case, it is negative 2x squared plus 8x minus 1. And what they're asking you to do is to find critical points, find increasing intervals, find decreasing intervals. Okay? So first, find the critical points, meaning f prime, take the derivative. So here's why you've been learning all the mechanics about how you find a derivative. Do you agree with me this is negative 4x plus 8? Are you okay with your rules? 2 is a coefficient, it stays. Negative 2 is a coefficient, it stays. The old power is a new coefficient. That's where you get negative 4. And the new power is 1 less. To subtract 1 is just 1. Then 8x, 8's coefficient, it stays. The derivative of x is just 1. And then any constant here, the derivative is 0. Okay. So there is our first derivative. Critical points are where the first derivative is 0. So what you do is you set the first derivative equal to 0 and solve. And you agree there's only one critical point at x equals 2. Negative 4 times 2 plus 8, that's 0. So there's only one critical point. And I'm going to want to plot that point. Remember, the goal is to be able to do a sketch of the curve. So the first thing that you sketch, the first thing you put on your picture is critical point. And so you need the y-coordinate when x is 2. When x is 2, what's the y-coordinate? Plug into f. That's negative 2. 2 squared plus 8 times 2 minus 1. Is that 7? 4, negative 8, plus 16 is 8, minus 1 is 7. I think that's 7. So I'm going to draw a graph here. One, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So when x is 2, y is 7. 1, 2, 3, 4, 5, 6, 7. So there I have a critical point at 2, 7. So I have one and only one. There's only one critical point. I want to convince you that one point chops the x-axis into 2 intervals. There's an interval on the left, there's an interval on the right. And each of those intervals is going to itself be all decreasing or all increasing. You agree with me? Over here on the left. If the graph went from increasing to decreasing, it would create a new critical point. So each of these intervals, once you've found all the critical points, the intervals have to all be the same shape. It couldn't change within an interval because it would create a new critical point. So here are your intervals. So here's your shape table. You have intervals over which you're going to test the first derivative to conclude something about the shape. So I have only one critical point, so I've got two intervals. Left of 2, right of 2. And within each of these intervals, each interval has to have the same shape. It couldn't change its mind. It created a critical point. So, take any number left of 2. It doesn't matter, let's say 1. Test f prime at 1 point. So I'm going to do f prime at 1. I could have used 0. I could have used any number left of 2. I pick 1. So here's my f prime. It's negative 4 times 1 add 8. Isn't that positive 4? What I care about is that it's positive, because that means my shape is increasing. If my derivative is positive, my shape is increasing. And here, to the right of 2, pick any number, let's say 3. Anything to the right of 2. What's f prime of 3? That's negative 4 times 3 add 8. Isn't that negative 4? Less than 0. Therefore, this shape is decreasing. And so what that means is you now can draw a rough sketch of what the curve looks like. This is only a rough sketch. If you wanted something more accurate, you'd have to plot more points. But the idea is just to get a rough feel for what it looks like. So let me take some colors here. How about blue? Oh, I don't know. I was doing orange and pink. So it's increasing on the left, and it's decreasing on the right. That's what the curve has to look like. And it sort of makes sense to you, right? Because you've got an upside down parabola. You know that x squared means a parabola. Because it's negative 2, it's an upside down parabola. So that makes sense. And just in passing, notice that there's no absolute minimum. Because the ends of the graph just get lower and lower and lower and lower. But we do have an absolute max. It's both relative and absolute. So we have an absolute max at x equals 2. Because that y-coordinate of 7, that y-coordinate is larger than all of the y-coordinates on the graph. So this is what you're doing in 5.2. You are looking at the first derivative, coming up with the shape intervals, and then drawing the picture, drawing a rough sketch. And I keep saying a rough sketch because, you know, if you wanted something more accurate, you'd have to plot more points. Like, when x is 0, do you agree with me the y-coordinate is negative 1? So if I was drawing this more accurately, I should have drawn it narrower like that. But that's what I mean when I say that what we're doing is a rough sketch. Okay? Let's do another one. So in your homework you have number 21. Let me do number 22. 5.1, number 22 on page 308. And so they just give us the function f of x is equal to x cubed plus 3x squared minus 9x plus 3. Okay. And in general, remember the comment I made at the very beginning? We had a cubic curve in the first problem. And you remember I said a cubic curve in general looks like that sideways S. Looks like that sideways S. In general, that's as complicated as degree 3 could be. You could have simpler though, right? Do you know that if you only had x cubed, if that was all the curve you had, do you remember that it looks like this? Comes in, flattens out, goes up. So the sideways S curve is as complicated as it gets. It might be easier, could be easier. So because this is degree 3, we have in the back of our minds, more or less what the thing looks like. But what we do is take the derivative. 3x squared plus 6x minus 9. And you set that equal to 0 in order to find the critical points. Well, how good are you on your factoring? First, do you agree I could factor a 3 out and I have x squared plus 2x minus 3? Here you have a trinomial. FOIL, first outside, inside, last. How are you in factoring these? That factors into x, 3, 1, plus, minus. And you want to know when is that equal to 0? Well, the only way a product is 0 is if the factors are 0. Now, 3 is just 3. 3 is never 0. It's just coefficient. Doesn't affect anything. But here, x could be negative 3. That'd be a critical point. Or x could be positive 1. We've got 2 critical points. And so we're going to want their y coordinates. So I've got x equals negative 3, that's one of them. And then I have x equals positive 1. I need the y coordinate. In other words, I need to take negative 3 and put it into f. Okay. It's only arithmetic. Negative 3 cubed plus 3 times negative 3 squared minus 9 times negative 3, add 3. Well, isn't that negative 27, isn't that positive 27? Well, those cancel out. And here I have negative, negative, that's 27, and 3 is 30. So I came up with a y coordinate of 30, and over here, the y coordinate f of 1, plug 1 into f, 1 cubed plus 3 times 1 squared minus 9 times 1 and 3. So 1 and 3 is 4, minus 9 is negative 5, add 3 is negative 2. Did you get negative 2? So there are my 2 critical points. And I need to graph them. And notice 30 is a big number. So you can in order to accommodate big numbers, you can scale your axes differently. So let's say here, let's scale the axis in 1, 2, 3, -1, -2, -3. So I've scaled the x-axis big, but now on the y-axis I need to go up to 30. So how about if I scale it in tens? 10, 20, 30. So this here would be -10. So when x is -3, y is 30. There's a point. There's a critical point. And when x is 1, y is -2, like right about there. Now at this point, remembering what I said about a sideways S, at this point you can guess, but you still need to write out the intervals anyway. So if you know that these are critical points, wouldn't you guess that it probably looks like up, down, up? Yeah, sideways S curve like that. You're right, but you need to write out the intervals. So now we're going to do our shape table. Over which we're going to test the first derivative at one point to conclude something about the shape. So I need intervals. And do you see if you have 2 critical points, you have 3 intervals? If you have 3 critical points, you have 4 intervals, right? Always one more interval than critical points. Think about it. If you have a piece of string and you make 3 cuts in a piece of string, don't you get 4 pieces of string? So it's always one more interval than critical points. So here, you got an interval which is left of -3. You got an interval which is between -3 and 1. You've got an interval to the right of 1. And so let's test f prime in each of these intervals. Now, let's take any number left of -3. How about -4? Now here's a shortcut. You could go back to f prime and stick in -4 and do the arithmetic. How about a shortcut? You see, you only care whether f prime is positive or negative. You don't care numerically what it is. How about if you go back to the factored form of the first derivative? That's your f prime right there. And so if I want f prime of -4, what have we got? -4 plus 3 is -1, that's a negative number. And -4 minus 1 is -5, that's a negative number. If you multiply two negative numbers, you get a positive number. I can go back to the factored form because I don't have to do the arithmetic. All I need to do is ask, okay, does it turn out to be positive or negative? And so the shape is increasing. Now between -3 and 1, pick any number you want. How about 0? And again, all I care about is the sign. So imagine putting 0 in for x. Remember, 3 is just 3. put 0 in for x, you get 3 times negative 1. You have a positive number times a negative number. And a positive number times a negative number gives you a negative number, so that's decreasing. And here in your third interval, pick any number you want to the right of 2, say f prime of 2. If you put 2 into here, you have 5 times 1. A positive number times a positive number gives you a positive number. And so you have filled in the shape table, and so you know on the left it's increasing, in between it's decreasing, and on the right it's increasing. There's your rough sketch according to the shape table. Okay. We have 10 minutes. I could do another problem, but how about if I first ask you, Friday is our midterm. Is there anything you'd like to ask me about the midterm on Friday? Yeah.
Could we do a problem of like, with like interest, the interest problem?
Yeah.
Thank you.
Yeah. Because indeed, you know, I can tell you have looked at the study guide and you see there is some kind of interest problem on there. You remember we did talk about interest at the beginning of the course. And so remember we had some formulas there. If you have annual interest, of, let's say, R%. And so when I say annual interest, that means you compound once a year. And so if P is your deposit, in other words, P is principal, it's the amount of money you start with, your principal. And if T is how many years, the amount is P times 1 plus R to the T power. And I'll do a problem in a second, but let me also remind you, remember we talked about continuous compounding? This is where that E thing comes from. Continuous compounding for T years at R%. Then A is equal to P e to the RT. So remember, those were the couple of interest formulas we had. So let me do a problem now. At 7% annual interest, so when I say annual interest, I'm talking about this formula, right? So 7% annual interest, how long to double your money? You see my question? You can take your money and you can invest it at 7% compound annually. And you're gonna leave it there and let it compound year after year. How long until your money doubles? So how long? That's a question T, right? T is your time, how long? So your amount is to be double what you started with. And you start with P, 1 plus R, always, 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 always. Express percent is decimal, always, always. Always express it as a decimal, raised to the T power. And so is it clear? You can divide P out of both sides, which means that whether you start with $1 or whether you start with $1,000, it takes just as long to double your money. Because it depends on the 7%, not on the amount of your original deposit. So here I've got 1.07 to the T power is equal to 2. Remember we talked about exponential equations? That the only way in general to solve an exponential equation is to log both sides. So if you got 1.07t is equal to 2, the only thing you can do is log both sides. Because now, remember that property 3, we call it property 3? If you've got the log of something to a power, that power can come down in front. So this is equal to T, log of 1.07 is equal to log of 2. Therefore, T is the log of 2 divided by the log of 1.07. And you don't have your calculators. So go ahead and stop. Stop there, leave it that way. It's about 10 years, but you don't have your calculators. So go ahead and leave it that way. Did that answer your question?
Yeah, thank you.
So, yeah, be prepared. These were the two interest formulas that we talked about back in chapter 2, whatever. Anything else you'd like to ask about Friday's lecture? Yeah.
Can we go over one of the tangent line problems?
Yeah. So there was a problem where you need to find the equation of the tangent line. And so you remember the slope of the tangent is the hard part. The slope of the tangent is the derivative at the point. So let's say that we have a function f of x is equal to x squared plus 7x minus 4. And we want the tangent line at, well, let's pick a point. If x is equal to 1, y would equal what? 1 plus 8 minus 1 plus 7 is 8 minus 4 is 4. So I want the tangent line at 1, 4. So the slope is going to be given me by f prime. F prime is 2x plus 7. Right? F prime, x squared, 7x, 7, negative 4, it's a constant. So at that point, when x is equal to 1, that slope is 2 times 1 plus 7 is 9. And so here you've got, back in high school, you learned the equation of a line, right? Does this look familiar? Y minus y naught is equal to mx minus x naught. That was your so-called point slope form. Does that look familiar? Point slope form. You found that m is 9, and this point here is the given point x naught, y naught. So x naught is 1, y naught is 4. That make sense?
Mhm.
So the two bits you gotta remember. You gotta remember the slope is the derivative, and you sort of have to remember point slope form. Okay? So Friday is our midterm. Good luck. See you Friday.